Thank you so much for coming out. It's a great pleasure. This is a real. It's exciting to be able to talk about time travel with you. It's exciting to be able to discourse about good time travel, bad time travel. I'm not going to talk specifically about Primer, but I am going to give you a few hints in terms of my designs for time machines, or time machines that I think are good designs, and which ones are going to overlap with those from Primer. I don't want to ruin anything from the movie, and there will be time for questions at the end. If the questions are, do you understand how all the time paradoxes work in Primer? I can tell you right now the answer is no. I may be a little better by the end of the movie, but it'll only be my second watch, so probably still no at the end of it. So, first and foremost, you are already a time traveler. By the way, just so you know, these little goofy cartoons, they were done by my co-author from this book, A User's Guide to the Universe. This is Jeff Blomquist. The quality of artwork here is far beyond my ability, but you know, the idea of the cartoon is accurate, right? You are already a time traveler. You are traveling through time. You travel through time at 1 second per second. You are doing it all the time. You travel through space as well, but we travel through space far more slowly. To give you a sense, the moon, for example, is 1 light second away, and you are never going to get to the moon in 1 second. So we travel through 1 second in time real easily. We travel through 1 second in space really, really hard. But more importantly, we only travel to the future under normal circumstances. But now, one of the things that we discovered, and we discovered this more than a century ago, Einstein discovered, I mean, not, you know, regular dumb people like us, but Einstein discovered a century ago that it was possible to travel into the future at different rates. He found that if you started traveling really fast, and by really fast, I mean the standard here is not, you know, 60 miles an hour or even 1,000 miles an hour, but fast compared to the speed of light, to a beam of light. If you start going close to the speed of light, what will happen is your internal clock, your heart rate, or, you know, if you're wearing a watch, or if you have a computer clock, or any type of measurement that you can possibly do, it will start running slow. This is sort of meant to be science. It's meant to sort of impress you with the idea of science, but it's one of our first direct measurements of this. We can, you know, particles are created in the atmosphere all the time, basically when they're hit with other particles from outer space, and they come down to Earth. And most of them decay pretty quickly, and in fact they should decay so quickly we should never be able to detect them on the Earth. But they're traveling so fast that their internal clocks are slowed. And so they don't know that they're supposed to decay, and so far more of them reach the Earth than are supposed to. They're slowed down. And so this idea that you can slow time makes for one of the most famous thought experiments, the so-called twin paradox. And sort of here's a little goofy, here's supposed to be a goofy little animation, if I'm not clever enough to make it work. There we go, now it's an animation. Look at that. You can be a physics professor and apparently can't make a little movie work. Made the movie, though. The idea here is that you can send a spaceship, a little picture here is supposed to be Alpha Centauri, and if you take a little spaceship from Earth to Alpha Centauri, and you've got one person on the spaceship and you've got one person staying home, the person who stays here on Earth, they age, in the little numerical examples that I gave, 11 years, and the person who went on the spaceship, because they were going so fast by the time they were traveling along their trip, just because the numbers happened to work out, they aged almost 7 years, about 4 years less. And the reason it's called the twin paradox is you send two twins, one stays on Earth, one goes out into space at high speeds, and lo and behold, even though they started off as twins, one of the twins is now younger. Now this is kind of time travel. You're still both going forwards in time, but one of them's going more slowly. It's time travel, but it's bad time travel, right? You don't have a particularly good time travel movie if both of you are just going forward in time, but one's going a little more slowly. You can do some interesting things with it, I suppose. You can, for example, if you've got an extreme case of slowing down time, you can have some interesting effects. There's a famous quote by John Archibald Wheeler. Here's a picture of him. There's Wheeler, there's Einstein. Wheeler said, space-time tells matter how to move, matter tells space how to curve. And one of the famous examples of things that can cause matter to space to bend is this idea of a black hole. So we've got a black hole at the center of our galaxy. There's a picture of it, or a picture of the stuff around it. We can't actually take a picture, but it's so energetic. There's stuff falling onto it, and it gets very, very bright. Here's sort of an artist's conception. If you know one thing about a black hole, they're supposed to suck everything in. But the idea is that around a black hole, space gets so curved that time itself basically gets screwed up. And so here's another version of the same basic idea. Different effect, but same basic idea, that you can slow down time given the right circumstances. So near a black hole, time really does run slow. So for example, this is from Interstellar, another sort of classic example of making time run slow using the effects of, again, real actual physics. Again, cool science fiction, but not really what you're looking for if you're looking to do something like time travel. Because to be clear, if you come to a time travel movie, you are looking to go back into the past. You are looking to undo a mistake. You are looking to make a better version of yourself. You are looking to kill Hitler. You are looking to whatever. Do something different, perhaps. And none of that happens just because time gets slowed down. So what can we do about that? Well, here's a possibility. So besides warping space, like John Wheeler suggested and Einstein suggested, the possibility exists, maybe, and now this one's really speculative, because black holes exist. This one may not. The possibility exists that not only can you warp space, you can break it entirely. So this is something you may have heard of. This is something called a wormhole. And the idea of a wormhole is basically you create a shortcut through space. You basically have something that near it, it looks a little like a black hole. Space gets bent. But that basically you pop in one end and you come out the other. And in principle, you can take those mouths of the wormholes and you can move them around, and they're your little transportation devices. And at first, this doesn't seem like it's particularly related to time travel. It seems like it's related to space travel. But we've already kind of suggested that space and time are related to each other. And really, they are. So here's the idea. This is the same basic picture as before. But now, take our little spaceships, take our little twins paradox spaceships, and what they're doing is they're taking the mouths of these wormholes, and they're moving them between two planets far away. These two wormholes used to be synced up. They used to be twins. You go in one mouth of the wormhole, you come out the other at the same time. But now you go in one mouth of the wormhole, and you come out the other mouth of the wormhole 4 years later. It's a time machine. And it's a time machine into the past. And it's a real time machine that is consistent with the laws of physics, almost. And I say almost because, well, you need to be able to make a wormhole. That is the only missing piece. And we almost can make a wormhole. People have been thinking about a wormhole for a century. And we kind of have a model, except for, a couple of small problems. We do not know how to rip a hole in space-time. If you know how to rip a hole in space-time, you will win a Nobel Prize. You will be able to build a time machine, and I think those two things combined mean that you will be able to accomplish all your hopes and dreams. I think either one of those may mean you'll be able to accomplish all your hopes and dreams. We don't know how to do that. Partly we don't know how to do that because doing so requires something that we just call exotic energy. And if you think you're just calling something exotic energy because you have no idea what it is, you are more or less correct. Exotic energy is something, physicists call things like this all the time. We have exotic energy. You may have heard of dark energy or dark matter. These are things that we give names to, and we may have one or two ideas of the properties of them. We don't really know what they are. And so we give them a name, we say they have these one or two properties, and after that we just sort of call it a day. And so exotic energy is this stuff that sort of has negative energy somehow. We don't know how to make it, we don't know whether it can exist, and the general consensus is that it probably doesn't exist. So that's the bad news. But I'm going to pretend for the rest of this talk that it does. So, suppose we could make such a time machine. This is the most generally accepted version of a time machine we could make. What would the rules be? Well, it turns out that these are the same sorts of rules that you get in a version like Primer, in some of the best time travel fiction that we get. And by the way, these are the rules that I like. These are the rules for time machines that show up in physics. You can do whatever you want in your own stories. Go nuts. This is not meant as a judgment call. This is just meant for mine. Number one, these sorts of time machines will produce only one self-consistent version of history. There's only going to be one timeline. Number two, you will notice that when you were having these mouths of the wormholes, have a ball go in and another one come out beforehand, you couldn't do any of that before the wormholes were created. So you can't visit any time before you've created the time machine. So why aren't we visited by time travelers? Well, because we haven't invented time travel yet. And likewise, and this is just sort of a statement, sometimes people get really into certain movies. This is not again a judgment call. Certain movies are very popular, but they basically involve parallel universes. Well, this doesn't involve parallel universes at all. And as far as I can tell, parallel universes don't seem to exist. So again, this goes back to just one timeline. Okay. So if you're thinking, well, come on, you're putting a damper on things, I will say that there are physicists who are definitely worse. Hawking basically said there is a chronology protection conjecture. He basically said, no, there's no time travel at macroscopic scales, and called it a day. I don't want to be that much of a wet blanket. But I do want to make sure that we try to address some of the major issues that show up in time travel. Some of them that most time travel models need to address. There's the grandfather paradox. This is one of the most basic of them. You've got some sort of time machine. You go back in time accidentally or intentionally. I will give you the benefit of the doubt and say accidentally. You go back and you kill your own grandfather. You prevent your own birth. And this is obviously a paradox, and the question is, how do you resolve such a thing? This is something that shows up in a lot of fiction. It's something that seems inconsistent with the models we talked about. It's easily fixed with parallel universes, but again, those don't seem to show up in real relativistic models of time travel. Here's another one, and this isn't necessarily a paradox. This is something that could actually work, which is one of the viewers today was talking with beforehand was asking about my favorite time travel model. It happens to be the Terminator. You've got a very consistent time travel loop, and part of the problem with the time travel loop is why ultimately do the events of the Terminator take place? It doesn't make sense because the events of the Terminator themselves, sorry to ruin a 40-year-old movie, but the events of the Terminator themselves wouldn't happen unless the events of the Terminator had already taken place. This seems like a paradox, but to be perfectly blunt, and the way that he argued it was, look, it's not that there's many, many universes, but there's lots of ways that this universe can figure itself out. And so the only way this universe will figure itself out is that other ball, the blue ball, is going to come out in a way that it doesn't block the shot. It's going to deflect that red ball just enough so that the blue ball is going to come out in just the right way so that everything's going to be self-consistent. And lo and behold, after a lot of trial and error, that's exactly what happens. That you can go through and you can basically have models of time travel in which your actions, and this is with just a ball going in and a ball going out, but the idea is that you end up with time travel models where your actions just affect past you in exactly the right way so that everything ends up self-consistent. And to be blunt, that's the version that I subscribe to. Okay, so you've got this very nice little self-consistent view of the universe. What good is time travel then? Well, there's a few versions of this that end up being nice. You can create a self-fulfilling time loop, and a lot of them end up being good. You can win the lottery. Because guess what? Maybe you always have won the lottery in this time loop. If I go back, I find the winning number, nothing prevents me from having said, oh, I actually always had the winning ticket. You can go and see things that other people have never seen. You can read and copy the Library of Alexandria. Well, at least in principle, the time machine had already existed at that point. You can get information, you can have experiences that other people wouldn't be able to have access to. Okay, so that's all I wanted to say about time travel into the past. One thing I wanted to say about the future, which is tonight, we just happen to find ourselves with a little opportunity. Tonight, after midnight, look up if you have an opportunity, because there is a blood moon lunar eclipse happening right after midnight. Pi Day lunar eclipse, what a great opportunity. So please do take a look at that as well. But thank you very much. I am sure people always have great questions about time travel. Please let her rip. I'm very happy to answer any questions you guys have about time travel, real or imagined. Thank you very much.